deep beneath the serene, rolling hills where France meets Switzerland at precisely 2:47 a.m. on March 15th, 2025, the CMS control room at CERN hums with a quiet intensity that belies the monumental moment about to unfold. The air is thick with the soft drone of high-powered computers and the gentle whir of cooling fans, a symphony of human ingenuity probing the unseen realms of the subatomic world. Scientists, their eyes heavy from long caffeine-fueled shifts, monitor endless streams of data pouring in from the Large Hadron Collider, LHC, unaware that this night will carve its mark into the annals of scientific history. Suddenly, an unsupervised autoencoder algorithm, a tireless digital sentinel trained to recognize patterns in millions of routine proton collisions, flashes a jarring alert. Event 847,293 freezes every conversation in the room. On the main display, two muon tracks materialize like phantoms 43 centimeters from the collision point, with no visible parent particle or trails connecting back to the beamline. An astonishing 268 giga-electron volts of energy has vanished, carried away by an invisible entity into the void. This isn't merely data, it's a potential window into the elusive realm of dark matter, a cosmic enigma that has taunted scientists for decades, promising to redefine our understanding of the universe. Dr. Sarah Chen, the shift leader, feels a chill ripple down her spine as she stares at the glowing display, her coffee long forgotten, now a cold relic in her trembling hand. Her mind races through a cascade of possibilities, each more exhilarating and daunting than the last, as the weight of a potential breakthrough presses against her chest. "Run the cosmic ray filters again," she commands, her voice steady but laced with an urgency that betrays the electric anticipation in the room. The operator, his fingers dancing over the keyboard with practiced precision, responds, "Already checked." This isn't cosmic, his hands betraying a slight tremble that mirrors the adrenaline surging through the team. Every system checks out. No beam halo contamination, no pileup interference, no hint of malfunction. The CMS detector upgraded for Run 3, which, as of October 1st, 2025, continues its extended operations until mid-2026, boasts a displaced muon trigger system engineered to capture such elusive signals with unprecedented precision. This technological marvel, meticulously designed to detect particles appearing far from their origin, has performed with flawless accuracy, potentially unveiling a textbook signature of dark sector physics, a hidden realm where invisible particles dance just beyond the grasp of our current understanding, teasing the boundaries of known science. As the event reconstruction unfolds on the glowing screens, a heavy silence settles over the control room, broken only by the faint hum of machinery and the rapid tapping of keyboards. The weight of the moment is palpable, like a storm gathering on the horizon. This could be the discovery particle physicists have chased across generations, a fleeting glimpse into a hidden world that could rewrite the laws of nature. The data paints a vivid picture. A heavy particle, born in the fiery collision of protons within the LHC, traveled 43 centimeters before decaying into visible muons and invisible fragments, with a lifetime of roughly 10 to the minus 12 seconds. This aligns with uncanny precision to predictions for weakly interacting massive particles, the leading candidates for dark matter. Phones buzz incessantly as WhatsApp groups explode with messages from theorists in London, Munich, and beyond, each frantically running calculations to test the implications of this anomaly. Has ATLAS seen anything similar? Chen asks, her voice slicing through the tension like a blade. The analyst, juggling 3 keyboards with the dexterity of a seasoned conductor, confirms that ATLAS is in an emergency session, grappling with the same question. Outside, the French Alps awaken under the soft glow of dawn, painting the sky in hues of pink and gold. But inside, hearts pound faster than the superconducting magnets humming 27 kilometers away in the LHC's vast underground tunnel. The stakes are monumental, promising a new chapter in humanity's quest to understand the cosmos. Zooming out from the confines of the underground control room to the boundless expanse of the cosmos, dark matter emerges as the universe's silent architect, a mysterious force that shapes the very fabric of reality. According to the latest cosmological models in 2025, it accounts for approximately 27% of the universe's mass energy, dwarfing ordinary matter by a ratio of 5:1, a testament to its dominance in the cosmic hierarchy. This invisible substance acts as the gravitational glue that binds galaxies into into their majestic spirals, preventing stars from drifting apart like leaves scattered by an autumn wind. It weaves the intricate cosmic web, connecting galaxy clusters across billions of light years, sculpting the large-scale structure of the universe. For over 80 years, scientists have pursued it with relentless determination, deploying underground tanks filled with ultra-pure liquid xenon to catch the faintest nudge from passing dark particles, launching space telescopes like Fermi to scan for gamma-ray glows from annihilations in galactic cores, and smashing protons at near-light speeds in colliders like the LHC. Yet, until this moment, all searches have returned empty-handed, yielding only tighter constraints that fuel an unyielding resolve to crack the mystery. This displaced muon signature, a displaced vertex paired with missing transverse energy, fits seamlessly into dark sector theories, offering a tantalizing clue to a hidden realm of particles that interact with our world through rare, fleeting portals, challenging everything we thought we knew about the universe. How did a machine uncover what human intuition might have overlooked? The answer lies in the unsung heroes of modern physics: unsupervised autoencoders, neural networks that tirelessly sift through millions of proton collisions with superhuman precision. These algorithms construct an intricate map of the mundane: jets of particles spraying like fireworks, energy flowing in predictable patterns, trajectories following the rules of standard physics. When event 847,293 arrived, the reconstruction error spiked like a siren piercing the night, signaling an anomaly that defied every learned pattern. Two muons materialized from nowhere, with 268 giga-electron volts of energy vanishing into an unseen darkness, a signature that fell far outside the realm of ordinary physics. The autoencoder flagged it instantly, not like the others. Human physicists then launched a meticulous assault, systematically dismantling every possible mundane explanation. Cosmic rays were ruled out. The muons originated within the detector's volume, not from atmospheric showers above. Beam halo particles were eliminated, as timing stamps confirmed stable beam conditions with no stray protons. Detector glitches were debunked. Muon chambers, calorimeters, and energy calculations aligned with perfect harmony. Pileup was improbable in low luminosity runs, and statistical flukes were calculated at less than a 1 in 50 million chance. The anomaly stood resolute, a stubborn beacon demanding deeper scrutiny and igniting a spark of hope that we might be on the cusp of a scientific revolution. The CMS detectors run 3 upgrades, operational as of October 2025, and amassing nearly 200 femtobarns of integrated luminosity, have transformed the hunt for dark matter into a high-precision endeavor worthy of the universe's grandest mysteries. Displaced muon triggers, now capable of capturing particle pairs appearing centimeters to meters from the collision point, operate with staggering efficiency, a far cry from earlier runs where such events might have slipped through undetected. Before these enhancements, a 43-centimeter displacement could have been lost in the cacophony of standard physics noise, dismissed as an inconsequential blip. Now, it's spotlighted with laser-like focus, aligning perfectly with dark sector predictions. A heavy particle charged with some exotic properties zipping through the detector before splitting into visible muons and invisible fragments that carry away unmeasurable momentum. This leap in sensitivity, from missing 90% of such events to capturing the vast majority, turns faint whispers into resounding alarms, positioning CMS at the forefront of a potential revolution. The upgrades, meticulously engineered to probe the boundaries of known physics, have set the stage for a discovery that could redefine our understanding of the universe's hidden components and our place within it. The narrative accelerates with Atlas's upcoming trump card, the High Granularity Timing Detector, HGTD, set to debut with the High Luminosity LHC, HLLHC, after 2026, a technological marvel that promises to redefine the precision of particle detection. This cutting-edge system stamps particle tracks with an astonishing 30 to 50 picosecond resolution. Faster than light crosses the diameter of a single proton, offering a temporal microscope into the subatomic world. For our displaced muons, the HGTD would reveal microsecond differences in their arrival times, proving a sequential decay cascade if the signal is genuine, a hallmark of a real physical process. Background noise, such as pileup or cosmic interference, would betray itself with smeared, inconsistent timings, exposing its fraudulence with mathematical certainty. The HGTD acts as a lie detector for particle physics, transforming ambiguity into clarity and eliminating doubts about without pileup or detector artifacts. By confirming the precise temporal relationships of decay products, it holds the power to either solidify this anomaly as a groundbreaking discovery or unmask it as a fleeting instrumental quirk, pushing the boundaries of what we believe is possible and bringing us closer to the truth of the cosmos. Adding a layer of gripping tension to the hunt, the Higgs boson imposes a stringent ceiling on dark matter interactions, acting as a cosmic gatekeeper that narrows the scope of possibility. As of mid-2025, ATLAS and CMS global analyses, incorporating the full dataset from Run 2 and partial data from Run 3, have refined the Higgs invisible branching ratio to a tight 10.7% at 95% confidence, a sharper constraint than earlier estimates, reflecting the relentless accumulation of high precision data. For theories positing that dark particles couple to our world through the Higgs field, any detectable signal must be rare enough to have evaded prior searches, yet frequent enough to manifest in the high luminosity runs of the LHC. This delicate balance dramatically squeezes the theoretical parameter space, eliminating less viable models and sharpening the focus on those that hold promise. With fewer places for dark matter to hide, the hunt becomes a high-stakes game of precision where every new dataset brings us closer to either confirming a transformative discovery or refuting it as a statistical anomaly. The Higgs constraint, like a cosmic riddle, challenges scientists to refine their theories and experiments, heightening the anticipation of what lies just beyond our current understanding. The search for dark matter extends far beyond the confines of CMS, weaving a global network of detectors designed to trap the elusive cousins of our mysterious particle. FACER, positioned 480 meters downstream from ATLAS in the LHC tunnel, has already etched its name in history by detecting collider neutrinos, a feat once thought impossible. Its 2025 results, setting stringent limits on dark photon masses without detections, probe particles boosted forward with tremendous momentum, far from the central collision zones. If our event signals a dark particle family, related particles with longer lifetimes might decay hundreds of meters away, precisely within FACER's acceptance window. Unlike central detectors like CMS and ATLAS, which excel at capturing decays near the collision point, FASER is tailored to snare long-lived exotics that escape traditional detection nets. Together, these experiments, CMS with its precision triggers, ATLAS with its robust calorimetry, and FACER with its forward reach, form a comprehensive surveillance web spanning a spectrum of lifetimes and masses. This multifaceted approach ensures that no dark sector particle, no matter how elusive, can slip through undetected, creating a global dragnet that could finally corner the universe's invisible architects. Confirming a dark matter discovery demands a rigorous triad of evidence, a three-pronged assault that tests the signal from every angle. Make it, shake it, break it. First, colliders must reproduce the signal. ATLAS must mirror CMS's signature, with identical flight distances, energies, and timings across its independent detector systems. Real physics replicates consistently across experiments, while statistical flukes falter under scrutiny. Second, underground detectors like LEX Zeppelin or Xenon, buried deep to shield them from cosmic noise, must detect nuclear recoils matching the masses inferred from collider data, forging a direct link between lab-created particles and the cosmic dark matter pervading the universe. Third, space telescopes like Fermi must spot gamma-ray lines from dark matter annihilations in the dense core of our galaxy, with energies precisely aligning with collider measurements. These three witnesses, collider, Earth, and cosmos, form an unassailable case, each reinforcing the others to weave a cohesive narrative of discovery. If they align, the result is nothing less than a historic rewriting of physics, a moment that will echo through generations. The synergy of these independent methods transforms a single anomaly into a robust, undeniable truth, captivating the imagination of scientists and dreamers alike. Which confirmation excites you most? Lab, underground, or cosmic? Share your thoughts in the comments. A global cavalry of surface and beam experiments mobilizes to capture the elusive cousins of our potential dark matter particle. Expanding the hunt across diverse experimental landscapes with unparalleled ambition, Methuselah, perched 200 meters above CMS on the surface, is a massive tracking detector designed to detect ultra-long-lived particles that drift through hundreds of meters of rock before decaying in open air, offering sensitivity orders of magnitude beyond underground detectors like CMS or ATLAS. gas. Codex B, stationed at LHCb's interaction region, targets forward decays in quieter zones where background noise is minimal, optimizing for rare signatures predicted by exotic models like hidden valleys. Ships slated to begin operations in the early 2030s will probe the weakest possible couplings through proton beam dumps, patiently waiting for ultra-rare decay signatures that no other experiment can detect due to its unmatched intensity and background suppression. If our displaced muon signal represents a genuine dark sector particle, related particles with varying lifetimes and interaction strengths will appear across these diverse setups, each tailored to cover distinct corners of the theoretical landscape. This multi-pronged approach, spanning caverns, surface detectors, and beam dumps, ensures a comprehensive search, leaving no stone unturned in the quest to map the dark sector's intricate family tree and confirm the existence of a new realm of physics. Every anomaly must survive a relentless gauntlet of systematic checks, a scientific crucible designed to burn away imposters and reveal the truth with unyielding precision. Automated filters meticulously purge instrumental noise, ensuring that missing energy reflects genuine particle escapes rather than detector malfunctions or calibration drifts. Veto systems slash beam halo and cosmic ray contamination, using precise timing correlations and trajectory patterns to distinguish collision-produced particles from external interlopers like atmospheric muons that mimic displaced signatures. Control regions, carefully selected to mirror signal conditions but exclude genuine anomalies, validate background models by ensuring no unexpected excesses appear where they shouldn't, providing a robust check on the experiment's integrity. The signal's ability to endure this rigorous pipeline, surviving every cut while maintaining statistical significance, builds confidence exponentially, separating true anomalies from fleeting artifacts with methodical precision. Each check refines our understanding, either reinforcing the anomaly's reality as a potential breakthrough or revealing subtle detector effects that sharpen future searches. This patient, systematic destruction of false hypotheses is the bedrock of scientific progress, ensuring that only the most robust signals earn the right to reshape our view of the universe. The potential ripple effects of a dark matter discovery extend far beyond the sterile confines of the laboratory, promising to reshape technology and society in ways we can only begin to imagine. Much like quantum mechanics birthed transistors, lasers, and MRI scanners in the 20th century, dark sector particles could lead to revolutionary sensors exploiting novel interaction principles, diagnostic tools for medical applications that surpass current imaging technologies, or entirely new computing paradigms that leverage hidden valley dynamics to process information in ways we can't yet comprehend. While cosmic rays, bombarding Earth with energies far surpassing the LHCs, pose no risk of opening dangerous portals, they provide vast datasets that fuel this scientific chase, offering clues to the universe's deepest secrets. The timeline for such applications remains uncertain. Some discoveries translate to technology in mere years, while others require decades of development. But history demonstrates that fundamental breakthroughs consistently yield transformative innovations that redefine how we live. This pursuit, driven by an insatiable curiosity about the universe's hidden mechanics, lays the groundwork for advancements that could bridge the esoteric world of particle physics with the everyday lives of people across the globe, connecting the subatomic to the societal in ways we can't yet predict. The path to confirming this anomaly is a meticulous roadmap of replication and cross-validation, a scientific odyssey designed to transform a tantalizing hint into an unassailable truth that could redefine physics. Run 4 datasets, expected to begin in 2027 with even higher luminosity, will seek to repeat the displaced muon pattern with greater statistical power, either amplifying the signal's significance or exposing it as a fleeting fluctuation. The HGTD's 30 to 50 picosecond timing precision, set to debut post-2026, will dissect decay cascades with surgical accuracy, distinguishing real sequential decays from smeared background noise that betrays instrumental artifacts. Geometric precision, matching flight distances, decay angles, and momentum conservation to theoretical predictions, must hold within measurement uncertainties to rule out random distributions. Cross-checks between ATLAS and CMS, leveraging their distinct detector technologies, liquid argon versus crystal calibration calorimetry eliminate single detector biases, as their differing systematic errors make identical fake signals nearly impossible. Correlations with underground recoil limits from LEX Zeppelin or Xenon, and gamma-ray annihilation lines from Fermi weave a cohesive narrative across collider, terrestrial, and cosmic observations. The evidence mounts: off-vertex muons, 268 giga-electron-volts of missing energy, Run-3's enhanced triggers, the Higgs's 10.7% ceiling, and a multi-detector trap spanning caverns, surface, and beam dumps, all converging toward a potential paradigm shift that could echo through scientific history. The Large Hadron Collider, a 27-kilometer ring buried beneath the picturesque landscape of Geneva, stands as humanity's most ambitious tool for probing the subatomic realm, a testament to our relentless drive to understand the universe's origins. Accelerating protons to an astonishing 99.9999991% of light speed, it recreates the searing conditions of the universe microseconds after the Big Bang, when temperatures reached trillions of degrees and exotic particles filled the cosmos. Its 2012 discovery of the Higgs boson, a triumph that validated the Standard Model's final piece, earned global acclaim and cemented the LHC's place as a cornerstone of modern physics. Now operating at 13.6 TeV and pushing toward an unprecedented 3,000 femtobarns to the power of -1 in the HLLHC era, starting in 2029, the LHC is the ultimate instrument for chasing dark matter, probing energy scales where exotic particles may emerge from the chaos of proton collisions. Its 4 massive detectors, including CMS and ATLAS, capture the fleeting aftermath of these collisions, sifting through billions of events to uncover anomalies that could redefine our understanding of reality. This engineering marvel, blending cutting-edge technology with human curiosity, stands at the forefront of the quest to unravel the cosmos's deepest secrets, bridging the microscopic world of particles with the vastness of the universe. Dark matter is far more than a scientific puzzle. It's the invisible scaffold that shapes the universe's evolution, from the formation of galaxies to the intricate cosmic web spanning billions of light years. Comprising 27% of the universe's mass energy, it influences gravitational lensing, galaxy rotation curves, and cosmic microwave background fluctuations, providing undeniable evidence of its presence through multiple independent observations. Discovering its true nature would not only define new fundamental forces and particle families, but also revolutionize cosmological simulations by replacing speculative models with precise, lab-measured properties, offering a clearer picture of the universe's history and future. The technological spin-offs, though likely decades away, could transform society following the path of quantum mechanics, which gave us semiconductors, and nuclear physics, which birthed medical imaging and therapies. This chase connects us to the cosmos, bridging the microscopic world of particles to the vastness of space, and fuels innovation through the relentless pursuit of knowledge. It's a testament to humanity's enduring curiosity, a journey that not only seeks to understand the universe, but also promises to reshape our world through discoveries that ripple across generations. The hunt for dark matter presses forward with unwavering determination, each step a calculated move in a high-stakes quest to confirm or refute this tantalizing anomaly. Tighter data runs in Run 4, expected to launch in 2027 with increased luminosity, will amass higher statistics to test the signal's consistency, potentially elevating it to undeniable significance or revealing it as a statistical quirk. The HGTD's precision timing, with its 30 to 50 picosecond resolution, will dissect decay cascades with surgical precision, distinguishing genuine sequential decays from the smeared signatures of background noise. Surface detectors like Methuselah watching from above CMS and Codex B, guarding LHCb's forward region, will search for long-lived cousins with lifetimes spanning meters to hundreds of meters, probing exotic models that central detectors might miss. Ships set to probe ultra-weak couplings through beam dumps in the early 2030s will push the boundaries of sensitivity into theoretical territories previously inaccessible, potentially detecting particles that evade all other experiments. If the signal persists across these diverse platforms, platforms, corroborated by underground recoil measurements from LEX Zeppelin or Xenon and cosmic gamma ray lines from Fermi, physics textbooks will be rewritten, heralding a new era of understanding that could redefine our place in the cosmos. This journey, spanning years of meticulous measurement and international collaboration, invites us all to ponder the universe's deepest mysteries and our role in unraveling them. Which aspect of this cosmic chase captivates you most? Collider breakthroughs, underground detections, or cosmic signals? Drop a comment and join the quest to uncover the secrets of the dark universe.